Good afternoon, gentlemen. In today's lesson, we are going to look at the second fundamental theorem of calculus, and we're going to talk about why it's important, and I'm going to show you how it works, and give you some examples, and then I have created a Delta Math assignment that will allow you to practice some of this. So what is the second fundamental theorem of calculus? Sometimes, by the way, it's called the fundamental theorem of calculus part 2. And what it says is, it says if f of x is continuous. So if you have a continuous function on an open interval, containing A, where A is a constant, then for every x in the interval, if capital F of x is equal to the integral from the constant A to x of f of t dt, then the derivative of capital F of x, which means you're taking the derivative of that integral, okay, that is equal to f of x. That is what it says, right? So if your function is equal to an integral, where the bottom bound is a constant and the top bound is, let's say, x, okay, and you're integrating a function, the only reason this isn't f of x is because you can't have the variables match, all right? But if that is your function and you take the derivative of it, you go back to lowercase f of x, okay? So why is this important? All right, well, the big deal here is that it shows that integration and differentiation are inverses of each other, okay? Differentiation and integration are the inverses of each other. That's the big thing, all right? And let me type this in here. Okay, I don't need size 36. Let's make it a little bit smaller. Okay, so why is this so important? Okay, a little bit smaller here. All right. Okay. First of all, and most importantly, it shows that differentiation and integration are inverses of each other. Okay. In other, let's see. You could say something like it says that the differential equation where f prime of x, capital F prime of x equals lowercase f of x, has a solution for every continuous function of f. It says that every continuous function f of x is the derivative of some other function, in our case the integral of f of t, And it also says that every continuous function has an antiderivative. Okay, it says all of those things, but the big one is that differentiation and integration are inverses of each other. Okay, so now I want to look at how does it work. Okay, so how does it work? Let me get my pencil working here again. Sorry. All right, so how does it? All right, so let's say that I asked you to find capital F prime of x, and I'm actually going to ask you to do it using the first fundamental theorem of calculus and the second fundamental theorem of calculus. Okay, we're going to do it two different ways, and I'm going to show you how it works out to be the same. All right, so here is capital F of x. It's the integral from a to x. Let me give you an actual function, 2t dt. Okay, so if you saw that that was capital F of x, and I asked you to find the derivative of it, well, using the first fundamental theorem, you would actually have to integrate first. Okay, let me put give me just a second. Let me write down the whole thing. F of x equals the integral. Okay, you would have to actually integrate first because you need an answer for this, and then you can take the derivative of it. Okay, so let's remember how to integrate. Well, you keep the constant, you add a power, and you divide by the new power. All right, that's the power rule, basic power rule. Okay, and so of course we can simplify that, and then remember you're going to plug in your bounds. Okay, and so I'm going to simplify and plug in my bounds at the same time. I get t squared, but now I have to plug in x and subtract and plug in a. Okay, keeping in mind that a is a constant. All right, so that is what f of x is equal to. The question is asking me to actually find the derivative of that. So I take the derivative of x squared, and I take the derivative of a constant, which equals 0, all right? And there is f prime of x, okay? Now, if I repeat the process using the second fundamental theorem of calculus, so just copying down my function again, I can jump straight to the derivative, and literally the derivative gets rid of the integral and replaces the t with an x. As long as the bottom is a constant and the top is just x, the integral disappears and the t changes to an x. Okay, so again, as long as the bottom is a constant and the top bound is just x, the second fundamental theorem says if I take the derivative of the integral from a constant to x of a function with t in it, all I have to do is change t to x and I'm done. And you can see that you do in fact, whoops, that's supposed to be an x. You do in fact get the same answer using the first fundamental theorem and the second, okay? And so, but obviously the second was a heck of a lot quicker, okay? So now we're gonna do some practice just using the second fundamental theorem. All right, so now just use the second fundamental theorem of calculus to take the derivative. Again, I'm going to give you integrals, and so you are taking the integral of you're taking the derivative of an integral, right? So if I tell you that capital F of x is the integral from 3 to x, right? 3 is a constant, top bound is just x. It doesn't matter what the function is. It doesn't matter whether we need u substitution or any of that, all right? Because I'm asking you to take the derivative of it, okay? The derivative of it. All you have to do is change the t's to x's, and you are done. Okay? So here's another quick one for you to practice. All right, so let's say we go from negative pi to x, and I give you a trig function. All right, cosine of t squared, dt. Again, I'm asking you to take the derivative. That's important. You have to be taking the derivative of an integral. The bottom has to be a constant. The top bound has to be x. And if that is the case, the answer is the function with t changed to x. And you're done. Okay? Now, of course, it's a little bit different, all right, if the top bound is more than just x. So we'll start with that. And it's a little bit different if the bottom bound is not a constant. So we need to go through all of that. All right, but let's look at if the top bound is more than just x. Okay. Basically, it's kind of like the chain rule, okay? So let me give you an example. The bottom is still a constant, but now we have more than just x for our top bound. Well, you start off exactly the same, okay? Again, we're taking the derivative of this. And so whatever your top bound is, you replace t with it. And I guess I don't really need parentheses there. But the catch is that it's like the chain rule. If it's more than just x, you have to multiply by the derivative of what you plugged in. So again, it's like the chain rule. And then you simplify and put it all together. And there is your derivative. Okay? Let me do another one. All right, so here's my f of x. Again, it's an integral from a constant to a function of x, but I'm integrating a function of t, okay? And I'm asking you to find the derivative, all right? If I literally wanted the integral, you would have to actually do it, okay? You actually have to integrate and then plug in the bounds. All right, but because I'm asking you to take the derivative, you literally plug in the function of x in place of t. Be careful that t is cubed, but then you have to multiply that by the derivative of what you plugged in. Okay, and that would be 20x cubed. All right, and you would want to simplify that and put it together as best you can. That would actually require me to cube the 5 and the x to the 4th, but that's a multiplication. And then I'm going to multiply that by 20x cubed. It gets a little bit bigger. And remember, now you add the exponents. Okay? And then let me give you one with a little trig in it just to make sure that we're good on this. All right, so let's say f of x equals the integral from negative pi to x cubed of cosine squared of 2t dt. Okay, and again, I am asking you to find the derivative. All right, so all you're doing is plugging in x cubed in place of t, but then you have to multiply the whole thing by the derivative of x cubed. All right, well, what's the proper way to simplify that? That would be to move the 3x squared to the front. It just looks better because it is basically the coefficient, okay? And that's all you need to do if the top bound is more than just x, okay? Well, what if the top and bottom bounds are functions of x. That means the bottom bound is not a constant. Okay, well, that ends up being more like you kind of follow the process of the first fundamental theorem where you plug in the top one and then you subtract and you plug in the bottom one. Okay, so let me give you an example or two of that. All right, so let's say f of x equals, all right, the integral from x squared to x cubed of 2d dt, okay? And I'm asking you to take the derivative. Please, you have to understand I'm asking you to take the derivative, all right? Well, we're going to plug in the top bound in place of t. Because it's more than just x, we have to multiply by its derivative. That's like the chain rule. Then we're going to subtract, and we're going to plug in the bottom bound in place of t and multiply by its derivative like the chain rule. And then we can simplify. And we're done. Okay? All right. Let me give you another one. All right, so even with a trig function, if I'm asking you to take the derivative of the integral, sorry, that should be f of x. It doesn't matter what the trig function is. All you're doing is changing the t to the function of x for the top bound first, multiply by its derivative, minus, keep the function and change the t to the bottom bound times its derivative, and then simplify. Make it look nice. And you're done. Okay? Now, I'll be honest, if I was only going to memorize one thing that we talked about today, I would totally multiply. I would use this one, right? And then, but why would it work the same? Why would the other ones work the same? Okay, well, let's go back up here to one that has a constant on the bottom. Okay, well, even if I plugged that constant in, so even if I follow the same rule I just did, where I actually plug in the top bound times its derivative minus, and then I plug in the bottom bound times its derivative, because the bottom bound is a constant, I will always multiply that second one by 0, and that's why it always disappears. So as a shortcut, if the bottom is a constant, you never have to worry about it. But if you're going to memorize one way, right, if you only want to think about it in one way, then you plug in the top bound times its derivative minus the bottom bound times its derivative, and if it happens to be a constant, it will work itself out. Okay? And that's really it for the second fundamental theorem of calculus. And so I have created a homework assignment in Delta Math for this lesson entitled Second FTC Practice that you need to complete before our next class. And then our next video, I'm actually going to open Delta Math and look at some other types of problems that you can do with that kind of apply in the context of the second fundamental theorem and show you how they work. And then there will be a second Delta Math assignment.